Hi guys, this is a video about strings and integers, how they are represented in memory, and how to convert between those representations without using the standard library. Let us start with a simple quiz. Here we have 3 printf statements, and I want to know, what do these print statements print to the console? So size of 1, size of 12,345, and size of this big number. So let's see, we start the program and execute the first printf statement, and we get 4, because on my system ints need 4 bytes. So not surprisingly, perhaps this number also needs 4 bytes, and this large number also needs 4 bytes. So no matter how big your integer is, as long as you're still within the bounds of integer, all integers need the same number of bytes. Small integers and large integers. Okay, now if we change these integers to strings, to string literals, you will see different results. Let's see what happens then. So you can already see the strings represented here in memory. So the first string, as you can see, uses 2 bytes. The visible digit 1 and the invisible null terminator, \0. The next string has 5 visible digits plus a null terminator, so 6 bytes in total. And here we have 10 visible digits plus the null terminator, so 11 bytes in total. So you can see there has to be some kind of complicated conversion progress if you convert this number from string to integer or the other way around, because you need to compute different bytes. So maybe I can make this a little clearer. Here I've prepared a C++ function template hex dump, which I won't show you. You can pass any value that is printable, and it will print the value, as you can see here, 1, the type, I stands for int, and all the bytes that are in memory to represent this value. So you can see the 4 bytes for the integer 1 are first a 1 and then 3 zeros. And for the string 1, as you already saw here in scoreboot, you have 1 byte for the digit 1 and 1 byte for the null terminator. So it's an array of 2 characters. And if you print it to the terminal, it looks exactly the same, because the terminal, if you think about it, is just 2,000 or something characters, right? So everything you see in the terminal is a character. But us humans tend to interpret sequences of digits as one number, but as far as the terminal is concerned, this is just 10 digits or 10 characters. Okay, what about 12,345? Here you can see the integer representation. Right, if you convert this to hexadecimal, it should be 3039. And the only reason these bytes are reversed is because I'm using a little endian system. So on PowerPC or Spark, you will see a different byte order. Okay, and the string is relatively straightforward. Here's the null terminator at the end, and then you have 5 digits. And these values are the ASCII codes of the digits in hexadecimal. So this would be 49 in decimal, 50, 51, etc. So the digits have the ASCII codes 48 to 57. You can look this up in any ASCII code table. Okay, next example is this big number that we already saw here. So all 4 bytes are different from 0 in the integer representation, already quite a big number. So this is 499602D2. And again, string representation is relatively straightforward. Here you see the digit 1 at the beginning, and the visible digit 0 has the ASCII code 48 or 30 in hexadecimal, and this is the invisible null terminator. Okay, then we have another example. This is a very interesting number because it's the biggest signed integer. You can see in hexadecimal it's 7f. Shouldn't surprise you if you've dabbled with hex before. And of course, the string is still 11 characters, 10 visible digits plus the null terminator. And what happens if we look at the next number? It doesn't fit into an int anymore, so C++ says this is long, or depending on your system, long, or long 64, or whatever. So you can see now for the first time we don't need 4 bytes, but 8 bytes. Okay, and again we need 11 digits in the string representation. Okay, so now we want to write 2 functions. One function that takes a string and converts it to an integer. So if we must write a function that, given, for example, string to integer. Given this string with consisting of 11 bytes, should produce a single integer, which is this value. And then, after we've done that, we will go the other way around. Okay, so maybe let's start with this function, convert a string to an integer. Maybe let's start with unsigned integers to make it a little simpler. Let's call it string to int. Pass it, pass it a pointer to constant character. And okay, let's see, how would we test this function? We could simply say string to int, maybe start with 1 and assign this to some variable. And we would expect this variable to have the value 1. Of course, it won't work now, we haven't done anything. So let's call the function. You can see p points to the first visible digit, and we have to do something with the first visible digit. What happens if we simply copy this digit 1 into the variable a, or if you simply return it? So what happens if we simply dereference it and return the 1? Then we get an interesting result. We get the ASCII code of the first digit. Of course, we don't want to see the ASCII code. We want to see a value between 0 and 9. So this is an interesting exercise. So the value 48 should be converted to 0. The value 49 should be converted to 1. The value 50 should be converted to 2, and so on. And the value 57 should be converted to 9. So we could make a big switch statement. I've seen beginners do this, but we can simply, if you look at the difference between these two numbers, you can simply subtract 48. Let's see if this works. So what is 49 minus 48? This should be 1, and indeed it is. And if you don't know that 48 is the ASCII code of the digit 0, we can simply write the digit 0 here. This should give us the same result. Right. Okay. So this works for the first digit. So now let's think about more complicated numbers, or numbers consisting of multiple digits. So if we have this number, 1, 2, 3, 4, 5, this is really, if you think about the weight of the digits, if you will, this is 1 times 10,000 plus 2 times 1,000 plus 3 times 100 plus 4 times 10 plus 5 times 1. And we can rewrite this formula. Let me copy paste this. So instead of 10,000, we could say 10 times 10 times 10 times 10. Is this still the same? 1, 2, 3, 4, I think so. And this is 3 tens, and this is 2 tens, and this is 1 10, and this is no 10. Okay. Why did I rewrite it this way? Because I can still simplify it further. I can say this is 1 times 10 plus 2. Oh, I'm sorry, I don't need this. I can put it here. Times 10 and then we add 3, and then we multiply that by 10 and add 4, and then I'm sorry, like this and like this. Right, now I need some opening parents. 1, 2, 3, 1, 2, 3. So this should be the same. Let's see, the 1 is multiplied once by 10, twice, 3 times, 4 times, just like here. The 2 is multiplied once by 10, 2 times, 3 times, just like here. The 3 is multiplied once by 10, 2 times, just like here. And the 4 is multiplied 1 time by 10, just like here. And the 5 isn't multiplied by 10 at all. And we can even go further, and instead of starting with the 1 and making it a special case, we can start with a dummy value of 0, multiply that by 10, and add 1. So now you should see the general form. We start with a dummy value 0, and then each time we see an additional digit, we multiply by 10 and add the next digit. And if we see another digit, we multiply by 10 and add the next digit. And if we see another digit, we multiply by 10 and add the next digit, and so on, until we see no more digits. Okay, so let's start with the accumulator set to 0. This is our accumulator. And then as long as we are not at the null terminator, we multiply x by 10 and add the next digit, like this, and then we can increment. Okay, and when we leave the loop, x should have the right value. Okay, I already see a bug, but that should be interesting to observe. So we start with the accumulator at 0. Here we are. We are not at the end of the string yet. So we multiply 0 by 10, which is still 0, and then we add the 1. Should be 1, right? No, it's not. We forgot to convert from the ASCII code to the value that we really wanted. So again, we have to subtract the ASCII code. Let's see if it works now. Right, we start at 0. We are not at the end. We multiply by 10 and add 49 minus 48, which is 1. So x should be 1. Okay, and then we increment the pointer. We should point to the 2. Okay. Now, we haven't reached the end yet, so let's multiply by 10, which is 10, and add the 2, which is then 12. Okay, so after we have updated x, or x is effectively the number or all the digits that we have observed yet. We have observed these 2 digits, we haven't looked at the rest. This looks like the number 12. Okay, let's look at the next digit. It's not the null terminator, so let's multiply by 10, which is 120, and add the next digit, so 123. So we have looked at 1 to 3, which is the integer 123. So let's look at the next digit, still not the null terminator. Let's multiply by 10, so 1230. Add the 4, so 1234. There we are. Let's look at the next digit, still not the null terminator. So this will be 12,345. There we are. Let's look at the next digit. It is the null terminator, and we can return the value we've just computed. Okay, nice. So this will work for all valid unsigned integers. So if I pick some number that is too big, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this should overflow to some nonsense value. Let's see if this indeed happens. Maybe we'll skip until we see the last digit to make it a little faster. Don't see all the intermediate steps. Okay, so until now everything is fine. We have stored 999,999,999, and then we try to multiply by 10, which doesn't fit into an unsigned integer anymore. So we will get some cropped value, and then we add the next 9. So it will be some nonsense value. Let's see. Right. So this is definitely not the right number. Okay, so maybe as a homework for you, you should detect overflows. Homework, detect overflows. And maybe simply return from the function early or exit the program or whatever you deem sensible. Okay, that was already the first function. So pretty simple if you understand the trick. Start with 0 and each time you see a digit multiply by 10 and add the next digit. Very, very simple algorithm. Okay, what about the other way around? So we have an integer and we want to convert it to a string. Okay, so let's call the function returns a const character pointer int to string. This is the number that we want to convert to a string. And let's start with the same simple test maybe. So if we call int to a string and give it, the number 1, and when we then print that to the console, we would expect the string 1 to be printed. Okay. Now returning character pointers is rather unusual in C. Normally we would pass a buffer in, but for the sake of simplicity, let's do it like this. So let's make a character array. How large does it need to be? So the biggest number is 10 digits long. We need the null terminator, so 11 bytes in total. And we need to make this array static so it doesn't disappear when the function ends, because we want to return a pointer into this array. Okay, right, so I think the simplest case is filling this array completely and not a small number. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This is 10 digits. Which of these 10 digits can we get at simply? So if we again look at, do we have this example here somewhere? Here, right. So we have this number, and we want to, we have this number, and we want to generate this sequence of characters, and there is no apparent connection between these 4 bytes and these 10 or 11 bytes. So we can't just, I don't know, copy this byte here or copy this byte here or something. So is there any mathematical formula that will extract one of these digits? And indeed there is one. If you say x modulo 10, which of these 10 digits will we get? We will get the last digit, right? If you divide by 10, you get the first or the leading digits, all the digits except for the last one. And if you say modulo 10, you get the last one. So if we simply put this one in the last slot at 10, let's see what happens then. Start the program. Right, we don't return anything. Let's ignore the warning. So let's see where. Right, we have this array. X is this value, and a at 10 is. Oh, I'm sorry. It should be a at 9. 10 is for the null terminator. I'm sorry. A at 9 should be our last digit. So what happens now? Apparently nothing. We stored the value 0 at position 9, and there was already the value 0. So we don't really want to store the value 0, we want to store the digit 0. So again, we have to add 48. Let's see if this works. And there we are. Can you see the difference? If we store the value 0, we get the null terminator, the character with the ASCII code 0. And if you store 48, you get the visible digit 0. And if you replace this with some nonsense like 97, you will get the letter A. Okay, so always make clear to yourself, are you talking about the null terminator or the visible digit 0? We want the visible digit 0 here. Okay, so how would we generate the next number? We could simply divide by 10, then we would essentially cut off the 0, and then we can store the next digit at the next slot, right? And then we can cut it off again and store the next digit at the next slot. Let's see if this works. And if it does, we can transform it into a loop. So now x is still the original value. We store the 0 here, and then we divide by 10, effectively cutting off the 0. Here we are. Then at the next slot we store modulo 10 should be the last digit, this 9. There we are, we stored the 9. Then we cut off the 9 by dividing by 10. There we are. And then we store the 8 at the next available slot. There we are. Okay, and we can go on. So let's transform this one into a loop. Maybe let's do it with pointer arithmetic. So a pointer that begins at, I want to begin at the null terminator, and each time I want to store a digit, I go 1 to the left and then store it. So the p points to the last digit I stored. So let's start at a plus 10, and then we enter a while loop as long as x isn't 0. We don't really need to write this, but I find it a little simpler or a little clearer. I'm sorry. We decrement p, dereference the pointer, and then store x modulo 10 plus, this is the same as 48, you already know this, and then we divide x by 10. Okay. Right. So when this while loop finishes, p points to the leftmost digit, and we can simply return that. Okay. Right, now let's test it with a smaller number so we don't have to wait so long. So let's see, we start at a plus 10. Here you can see the pointer starting here, pointing all the way to the null terminator. X is 1, 2, 3, which isn't 0. So we store the 3 in the next available slot. There we are. And then we divide by 10, so x is 12. 12 isn't 0, so we store the 2 at the next available slot. Here we are. And then we divide by 10. Now x is 1, x is still not 0. So we store the 1 at the next available slot. There we are. Then we divide by 10, x is now 0. And there are no more digits to create, so we can simply return p. P points now to this 1, and so this pointer will effectively be passed to printf, and printf will print the string that we just generated. Here we are. Okay, so just for fun, what happens if we don't make the array static, just so you can see the difference. So right now you can see there's a special memory region for static variables where the variable a is located, and if I remove the static and start the function, start the program, you can see that the statics are now gone. There are no static variables in the program. A is now allocated on the stack inside of the stack frame of int to string, and if I return from the function, you will get an error that p, or that the return value points to something that doesn't exist any longer. Here we are, a dangling pointer. Okay. So let's make it static again. Right. Okay, so does this work for all numbers? What about 4, 5, 6, 7, 8, 9, 0? Does this still work? Start the program, step over the function. Right, still works. What about the biggest integer there is? Always check your boundary cases. Also works. Right, what happens if we pass the smallest unsigned integer, which is 0? What happens then? Start over. And now you can see that not a single digit is printed. This looks like a bug in our implementation. Let's see what happens. Let's step into the function. So again, we start at the null terminator. So while x is not 0, But x is 0. So we can't really distinguish between the cases where all digits are exhausted and x already starts out at 0. So what do we do here? So we have to execute this loop at least one time, right? We have, no matter what integer we put in, we want to have at least one character in the string produced. So is there a loop construct in C which guarantees at least one execution of the loop body? And indeed there is. It's the do while loop, right? So let's replace it with a do while. Okay, and see if it works now. So we point again at the null terminator and we immediately enter the loop and say the first available slot will be filled with 0 modulo 10 is 0 plus 48 will be 48. So I would expect a visible 0 to be generated here. And there it is, a visible 0 without the backslash. Then we divide 0 by 10, which is still 0, and we exit the loop. Okay, so the right number is printed. Okay, so this was comparatively simple, no hard edge cases except for the 0. So your homework will be write, how are these functions called? String to int, and int to string with signed int instead of unsigned int. So you will have to take negative numbers into account, which isn't quite as trivial as it might sound. So you should definitely test this with the smallest integer there is. Let me just copy this. So the smallest integer there is this one. You should test it with -1 is the biggest negative one, with 0, and with the biggest integer in the positive range. So make sure your solution works for all of these values. And if it doesn't work for this value, but it works for this value, then you have an interesting edge case, and you should think about how you could solve it. There are multiple solutions to this interesting edge case. Okay, right, so maybe before I end this video, I can show you the hexdump function in case you're interested. Maybe if you want to play with this further and want to see other kinds of values, how they are represented in memory. Okay, that's all for today, and I hope I see you next soon. Goodbye.